You're the man now.
Oh, I have to give a presentation?
Yeah. We don't have to, right? Do whatever you want. Doug's also, where is it? It's not even on here. The author of, what's it called? The Manning book. Oh, okay, well.
I wrote every
Look at that. So, memorize that. Cool. So, obviously, Doug is the reason you guys are all here today. We've got the ads up everywhere, even on the screen over there. I know I'm looking forward to sort of getting a better understanding of how NLP and all that sort of fits into the space of search engines. So with that, I'll show up and turn it over to Doug.
So my name is Doug Turnbull, and I wrote this book that I literally just got an email like 5 seconds ago saying it's really important to me, so it's exciting. So if you buy it in 2 weeks, I'm sorry, the book is shipping, I can guarantee it's 2 weeks. So check that out. What this book is about is the principles for getting more relevant search results out of Solar and Elasticsearch. How many people work with Solar and Elasticsearch? We've seen it. So, all right. So we're the second edition. I got a lot of candidates for second edition. So if you've worked with search engines, this talk might feel a little introductory. Don't worry, there's some good demo stuff I'm going to do after this. So yeah, that's an open source connection where I work. Use search, discovery, and relevance. And what that means is basically my whole job is to help organizations make search better so that they can improve their bottom line, whatever that is. It might be revenue per search for an e-commerce site. It might be all kinds of non-traditional search like enemy resolution, reducing the amount of false positives in vendor identification, for example, on a lot of data entry people. So that's basically what I do with Solar and Elasticsearch all day long. So, and this my company Open Source Connections, or our company Open Source Connections. Check us out. Check out the book. So I think there's a broad range of different sort of levels of search engine expertise. So I'm just going to kind of bring everyone up to the same level. So has anyone built a search feature using SQLite? Using SQLite? So like SQLite? Yeah, okay. I'll raise my hand.
We're getting you a mic, don't worry.
Oh, okay.
This is the one speaker we can't turn on.
Oh, okay. I could just scream. So what I want to talk about in this is why you use a search engine. Why is it such a good data structure? Especially for the NLP crowd, what does it do that a database doesn't? Why would you use MySQL, MongoDB to scan the website? And this may seem to the NLP crowd, to some of you, as an obvious case answer. But I think it's good to explore sort of exactly what is useful here. So let's just step back. Let's say we have, is everyone familiar with a science fiction Stack Exchange site? It's basically Stack Exchange question and answer. Science fiction, all the kinds of questions people would ask about science fiction. We want to find all the Darth Vader mentions in Stack Overflow. So why did Obi-Wan know about, what did Obi-Wan know about Darth Vader, where Reload started, and something, whatever. Two posts in our MySQL database. Now actually, what I've done here is I've loaded this data into a MySQL database. If someone comes up with a cup that's also a microphone, that would be $1 million admission. Test. Awesome. So we've got some stuff that I've loaded up into MySQL. What we want to do, our goal is to find it there, notice it's missing. So of course, this is the straw man that a lot of people like to beat up on, the SQLite operator. Scan all the rows for a match. And the SQLite operator is very much like paging through a book to find something, right? It does a table scan, it looks for each thing, looks for Darth Vader, and it's very slow, 300 milliseconds to do 20,000 documents on my fairly beefy laptop. And this gets worse linearly, right? So this is extremely slow, it's not fuzzy, it needs exact literal matching. MySQL is at least nice to do some more casing. And there's no fuzziness at all that people expect in search, like phrase matching or stemming or all the things that everyone here is very familiar with. None of that is built into SQL, right? And it's completely unranked. So some of you may have done Elasticsearch 101, build a search index. Create a search index and let's throw some documents at it. But what's actually being built? Well, what's being built on a search index is actually an index that's actually ordered in some conceptually in some lexicographic fashion that makes it easy to instantly jump to what we want to find. So we build that, we get Shakespeare at press. If we want to find Shakespeare stuff, we go to the SHs. We find we need to go to pages 30 and 31. Saves us the trip of having to scan through a book to find what we need. And that's really what a search engine does. Now, in Lucene, instead of necessarily having these concepts that were prepared by a professional indexer, right, that knows Shakespeare, knows Shakespeare, whoever that is, we have tokens, laser, that go to document IDs 2 and 4. Laser can be found in documents 2 and 4. Light can be found in documents 2 and 5. Lightsaber in 0, 1, 5, and 7, right? Okay. And what we're learning about, what I'm showing you here, is actually, it's 95% of the meat of what a search engine does. Oh, sorry. So the problem though is that computers are dumb, humans are smart. When we look at this index, we can infer a lot of stuff. And this sort of trying to create equivalences, equivalent classes between terminologies, it's a well-known NLP problem, right? We can see, with our knowledge of English language, we can see that cat and cats are the same thing. We can see that capital cat is the same as lowercase cats. We can see that kitty is probably the same as cat, sort of in the same idea. Feline, we are fancy, all those kinds of things. Computers, unfortunately, are dumb. All of these things to the search engine's index, the data structure that's sitting in the middle of the search record, are not at all the same. They're distinct UTF-8 strings. We're just comparing capital C and lowercase c are not at all the same character. So there's no matches between these things. Computers need exact character for character matching for something to be for a match. So, what happens? I'll walk over here with JSON is. You know JSON. What happens? What can we do to solve that problem? So, how many people here have written a Lucene analyzer before? So, 3, 4. So, Lucene and by extension Elasticsearch and Solr have this process called analysis. And if you're an NLP guru, you might say it's kind of like NLP light on a bunch of text. What analysis does, is it inserts a phase before the indexing. And as we'll see also before querying, it takes the text that we're going to index right up here, Darth Vader dined with Luke, and runs a normalization process on it. And if you walk through it, you can run this. This is basically, we're telling Elasticsearch, use this analyzer that is conscious of the English language. Snowball, the Snowball analyzer has some steps in it that are English aware. And give me the tokens that should come out of this. It's interesting. So if you look at Darth Vader down here, Darth, we get the first one in position 1, Vader in position 2, Dine in position 3, and Luke in position 5. Now, there's a couple interesting things happening here.
With was removed, so with is considered a stop word, so that goes away. And dying was stemmed down to dying. So this normalization process can also be seen as, if you're familiar with the idea of feature extraction, where we're actually extracting the features that are important about text. Dying here is a signifier for the idea of test. Okay. Dying is a signifier for the idea of dining with someone. Different representations, as we'll see, of dying all get stemmed down to a single representation. So instead of building that index, what we're actually building, and this is actually, you can tell we've seen to output this format. You can't actually tell Elasticsearch to output this format because it's locked down that interface, but you can do it in Solid. This is called the simple text codec. And the simple text codec was developed by Mike McCandless to take a search index and just output it to text so that anyone can sort of dig into how a search engine works. And basically, if it performs horribly, but it'll work, you can go in there and you can poke around with etc. and all the index files that you've seen Solid Elasticsearch. And you can see here that much like here we have an index with a bunch of terms, our index, Darth, has two terms, document 1 and document 2. And we've got metadata here about each occurrence of these terms. So, next step, and I'll walk over here where this text is. The next step is, is there anything we can store in that? What can we store in the metadata that can help us out? What can we store about an occurrence of some text in the document? Well, yeah, we can store the term frequency, and that's basically how much Darth occurred in document 1. And that's going to help us with relevancy linking. So how many people know about TF-IDF? So almost the whole group, so good. TF-IDF is basically a scoring algorithm for, if you don't know, that's basically how often did, notionally, if Darth occurred 5 times here in document 1, and 6 times in the whole index, which is 6 different documents in the whole index. And you have a 5 occurrences here out of 6 documents that have occurred across the whole index. That's more prominent. If Darth is very common, like hundreds and hundreds of documents, then that doesn't matter as much in relevance ranking. So that's one statistic that's stored there, along with a global sort of document frequency. And then we also, we've seen also stores positional information here. So Darth, what position did it occur? If Darth occurred document 1, position 4, and Vader occurred document 1, position 5, then that can let us do things like phrase matching, getting Darth in front of Vader. And that basically helps us support some of the fuzzy matching we might allow, what's called slop, where we switch Darth and Vader, tolerate a little bit of difference in position, if we want to do that. So, what happens when we query documents? And again, this presentation, basically, this is 95% of what a search engine does, and a lot of stuff outside of it is really syntactic sugar. Here's our query for completeness. User query. Okay, we've got the queries. Analysis on this side as well. And again, we'll see that we're doing basically a feature extraction. And I really want you to pay attention to this feature extraction part, because in a demo I'm going to run, which actually isn't a natural language demo, we're going to focus on how a search engine can really just be a generic feature similarity system. So, Luke, Darth, dinner. What's your analysis? Luke, Darth, dine. So dinner gets to this dine term. It's normalized down to a canonical representation. Each of these are consulted in the index. Darth, there, dine over there. We get a score for documents 1 and 2, score for document 1, and get results sorted by relevance back to the file. So that's basically how a search engine works. And I'm going to jump before I jump into a demo or two, I wanted to see if there's any questions. Some of this might be no news to me, but yeah.
So you mentioned TF-IDF.
Yeah.
What's better than TF-IDF? What's the new hotness?
So the new hotness is called BM25. I'm not sure it's always better than TF-IDF, but in document search, which is like
Paragraphs of text.
it's arguably better on generic corpuses in research. So whether or not it's better at your specific problem is completely different. Any other questions about, yeah?
What was that term again you cut out?
BM25, yeah, so we'll copy BM25, best match in 25, the 25th thing we tried. There's a lot of like, this is the nth thing we tried, and it seemed to return good, relevant results, like search relevancies. So, yeah. Yeah, so we actually we talk a lot about modeling taxonomies in the book. Google Whiteboard? But you can play with what a lot of people do is they model taxonomies with synonym files. So part of this process we can insert synonyms. So if we wanted to say that Darth Vader was a synonym of Anakin Skywalker, we can expand it. And a lot of people do this sort of semantic expansion where they will expand to parent concepts. So they will take maybe Darth Vader and Luke Skywalker and expand to Jedi. And that's actually a pretty powerful way to model taxonomies because the document frequency of Jedi becomes very large. It's not a very specific term, but the document frequency of these guys is much more specific. So if you're searching for, let's say we don't have any mentions of a certain kind of Jedi. We don't have Mace Windu here. We search for Mace Windu, at least we'll get some Jedi back, right? We'll get some sense that we understand what these are talking about. So. Any other questions or criticisms?
So I guess with that synonym file, is that something that you generate manually, or is we do that automatically using some other?
So some people manage it automatically. Some people usually you're creating it from an existing vocabulary. So as an example, there's the mesh vocabulary for that's out of NIH, sort of from medical text. But it's just a controlled vocabulary. You can write a little Python script and turn it to the right format so that something like Solar or Elasticsearch can understand it. I have clients who have, a lot of clients who have taxonomy databases. They have generated this from their database through crazy SQL queries.
I'm speaking of that. How often do you get brought over the client when we've got, like you said at the beginning, it was row scan, table scan based search engine?
These days, not as much. I would say a couple of years ago it was not uncommon.
Do you get questions like, why does it take, Google can search the entire internet in 7 milliseconds and it takes 45 minutes to search 100,000 records?
I mean, we get that with like open source search engines, or even in relevance. Why does Google understand everything that Google knows what I want before I ask for it? Why can't, and this is the reason that this talk is called The Ghost in the Search Machine is because a lot of people have very mystical notions of how search works. If you've worked with search, or you work with people with search who are non-technical, or if you're non-technical and use a search engine, it's hard to necessarily divide the difference between something like Solar and Elasticsearch, which is really more of a framework for building smart things, than Google, which is a complete implementation that's someone's invested billions of dollars into to make it really smart for. And web search is also a different use case than most people in search. So web search, you are focused very much on the idea of how much you can trust information. That's what page rank is so valuable. everyone was gaming all the original search engines back in the day with the keyword stuffing and craziness. So it's kind of somewhat of different problems. Any other questions? Yeah.
So, you were talking before about like ads, and you said kitty and all the other feline things. If you had a dictionary that mapped these things,
Sure.
what's the benefit or detriment in mind of having that additional information?
So by dictionary, you mean like every time or index time we expand the idea of cat to these
Yeah,
visual
I'm
ideas.
saying that cat is related to these things, kitty is related to these things, and it creates basically a map of the relationships of words.
So basically that's what synonyms do.
Right.
So synonyms would be like you could map cat to these other concepts. It basically comes down to a precision recall kind of thing, and how much you want to look at these things. So for example, if you just decided all these things were equivalent, if someone searches for cat, they might get feline as the first result and be frustrated. If you had a field that was a high recall field, which sort of matched from every possible interpretation of the cat, because you've mapped it to that, and you had a separate field or a separate query strategy that did something that was more focused on precision, where you wanted to match exactly what the user typed, then you could balance the relevance between those two. So you could, sometimes people do that at index time, sometimes people do that at query time with different queries to control how they're expanding the query. So, yeah.
What you've done with the domain specific taxonomy, do you find WordNet useful at all?
So I usually don't find WordNet useful for generic search problems. And there's a funny, so we did a project for Sears many years ago, and there was a funny thing where we came on and they just used WordNet or something for their synonyms. And someone would search for, I think they were searching for craftsman wrenches, and they were getting back artisan stoves. Something like that. I wasn't actually on this project, so didn't learn this. But yeah, so basically stuff like that happens, right? And especially if sometimes in certain domains, craftsman might be one company's brand and trademark, artisan might be another, or they might be like both selling stoves, for example. So those kind of things happen a lot. And so a lot of times, if you're really careful with synonyms, and sort of mindful of, when we do consulting, we go through this process of discovering our users' information needs, or their users' information needs. And there are times when it's very clear that if we could map maybe a technical language across to other similar forms of technical language, or less jargony or more jargony, or we need to map vernaculars between a lay audience and a technical content. I'm sure you've worked with law, so this is a common thing with that. Then we start thinking about how do we model these concepts with maybe a taxonomy or something like that, or other existing taxonomies. In other cases, it's not necessarily as useful, where people just literally want more string matching. And then there's a whole field of sort of I'm sure this crowd knows, sort of like topic modeling, sort of statistical measures, statistical and machine learning ways to derive taxonomies. So either possibly seeded with expert or pre-built taxonomies. Yeah.
We've struggled with the ability to test different versions of our search algorithm. So in a hypothetical, if you were to test game 25 versus if you had the luxury of split testing and tracking, what sort of success measures do you look for? How do you evaluate the effectiveness of one algorithm or another one?
So usually, first off, you have to understand what your users are after. Are they? Sometimes I've seen there's a lot of search that's just sort of like single item search, where it's like 99% of the queries are really zooming in on the one thing, and like I want to buy this one kind of thing. I'll check out. What kind of search is it?
That versus like just engaging with it. That's kind of structured. Not
page
good
depth.
thing, sometimes it can
Exactly.
be an indication of
It's certainly
not getting it ranked well enough.
Yeah, it completely depends on the information. So like, ideally you would have, do you have any kind of conversion in the mix, like something you're driving people to do, like a purchase or that sort of thing. So that might indicate that people had some level of success. So that's one way to do it. So a lot of what we do in A/B testing is we will identify sort of a pretty rough high-level business metric that we're comparing against. So we don't get like too far in the weeds of like click depth with that until we're trying to diagnose something. And often when we're trying to diagnose something, it's in the context of the kind of information you need. So click depth can often be a positive sign. There are times when click depth is not a positive sign, such as when you're often something, if a user is navigating somewhere else, like let's say they were frustrated with search and they went to the menu, that sort of thing, that could be no. Click depth after search is not so good. Things like paging, so paging through results. People often assume that's a bad thing, but we have a client in the U.S. Patent and Trademark Office who literally pages through every result because they have to verify that they basically don't have relevance ranking. They're just like and this is extremely common in legal search. Is everything here related to what I searched for? I need to evaluate each one expertly, so I can page and click every result. If this was e-commerce, that would be really great. So that's my consultant way of saying it depends. So, yeah.
Kind of piggyback off that, are there tactics to validate that the algorithm that you're building? Something that we've had a lot of challenges is that we're building an algorithm, but we don't know what we're getting back is correct or not, just because like the data sets too deep to.
So you don't have user data per se. It's like sometimes people don't have a lot of user data. Honestly, so we have this product called Cupid, Q-U-E-P-I-D. You should all go check out and buy. But what Cupid it's a search relevancy, test-driven search relevancy workbench. We go to Cupid, and Cupid, for a long time we had this idea of we were going to sit down with all their clients and they were going to click and tell us what good search results were. And it turns out that when we built Cupid, the test-driven part of it was really cool because we had all our searches that we want, sort of exemplar searches we want to optimize for, and we could tune Elasticsearch or Solar queries and kind of get close to quote-unquote what we wanted. But the harder problem beyond that, and the one that Cupid doesn't quite solve, it sort of just gives you a framework for you telling it about, is how you actually tell it about the quality of search results. And I've seen a couple different strategies. There's people who are very analytics focused, and that is very common in the e-commerce space, that are very deep into what their users are doing, and very sophisticated about how users are interacting with search. There's users who are running studies, like experimental studies. So a search application that is focused on physics researchers. There might be 50 in the world that care about, if you're like CERN and you're going to the physics wiki, the best thing you can do is if you can convince like some physicists to spend 4 hours with you, like load up all free donuts and Amazon gift cards you can, and like design a study for them. So that's the other side. And what you're looking for really is you're identifying information needs, which is basically an information need is what people you can look at their searches, but what people are looking for, and sometimes it's completely subconscious. So like an example we use in our book is Stack Overflow. I type in some error. Subconsciously, it wouldn't be that bad if I just found some code that like magically solved my error, right? So that's my subconscious need. But you're trying to triage these things because what you want to know is, are these information needs things that are, like I said, single item? Or are they get 3 or 4 things and compare them? So that's often common with product search where you're shopping around for Wi-Fi routers. Are they exhaustive? Are they, what are they exactly? And how often do key searchers in my engine fit into these categories? and that will basically dictate the analytics you use and how you study them. So there's a whole field, and if I was ever to write a 400-page book again, it would probably just be about evaluating search relevance. And in fact, the people that are much more sophisticated about, especially the analytics, tend to come more from a recommendations background. So if you really are interested, I would check out. There's the Manning recommendations on really book called Practical Recommender Systems. It's pretty good. So that's a little answer. Sorry. Yeah.
So something that's been conspicuously absent from your discussion of evaluations and what an academic evaluation is, which is having a gold standard and calculating a measure.
Yeah.
That's just totally irrelevant to what you do, or
No, actually,
So judgment, the tool I was talking about, Cupid, actually runs off a judgment list, but it's sort of like how you the ultimate output of what I was talking about is a judgment list. So a judgment list is basically a gold standard of like, here's a search query, and here are the results that are ideal. And we found just that the interpretation of judgment lists, also sort of like how you score whether how query performs against judgment lists, often is extremely specific. It depends a lot on the factors I was talking about. So there are like normal statistical measures called there's something called normalized discounted cumulative gain that measures relevance against the judgment list. But we've done that for some people, but we've also done like stuff that kind of makes sense to a non-technical person. Like, did this get my exact match and not get any of the other things? And we've even written just unit tests sometimes. Often because this is such a key point of collaboration between technologists and non-technologists, we often find that that something that makes more sense to people that are sort of more focused on the domain than the technology is often sort of helps. Sure. Yeah.
So there's just a question I have about whether search engines would still use some form of word frequency analysis in order to search so they would narrow down the search query as quickly as possible by searching for the least common word first.
Yeah, that's actually a common strategy. So that's if you were to run an AND query, if that happens. So basically, an AND query in Lucene, which if you have, there's kind of depending on how much data you have, usually you want to either have mostly OR query or mostly AND query. But an AND query works that way, where it's basically start with the thing that's the most rare. All right. Okay. Then we've limited down to 6 documents, for example, and then keep going. And then beyond that is the ability that a lot of people do where they're like, I didn't get any results, let me remove one of my search terms. Sometimes you remove the thing that is not at all present anywhere. So that's another strategy. So. Sure, yeah.
Bombarded, but
no problem. I like being bombarded.
I figured on your discussion of seers with craftsmen, do you encounter many occurrences whereby people want to mix case sensitivity with case insensitivity? Case insensitive with red and the case sensitive sort of window results, make sure that they're looking into the craftsman tool.
Oh, that's a good question. So like I can imagine one case where that really matters would be like searching code. Case sensitive identifiers. That's totally possible. So what you could do, and actually Elasticsearch is really good for this, because Solver is kind of annoying, and you can only specify one query analyzer unless you get into it. You could have an analyzer at query time that doesn't do lowercasing. That keeps the casing. You have one query that in like a Boolean expression that's based on that, and another query that's based on sort of a looser hierarchy call, like just lowercasing. So, yeah.
Or you have a search engine that is named entity sensitive.
Yeah.
Recognizes the difference between capital C, capital C, and lowercase.
That's a really good point. So wait,
So yeah, before you get here, you might do some identity extraction to know where all your brands are.
possibly throw those in a completely different field, or do that.
Every time that you're searching for a certain brand, that's what it is.
Yeah. So, any other questions? If anyone has any, like to throw me search engines. Yeah.
So, I was listening to John talking to you before. How much benefit do you get from looking at story logs for what people are searching for versus talking?
So it's kind of like an analytics versus like in-person discussion, quite a bit, because often I've been to clients where I sit down and I talk to like, sort of people, the non-technical sort of people who maybe they're merchandisers or they're content experts, content curators, and they have a mental model of how search works based on maybe who's complaining to them. Not necessarily based on what users are actually searching for. So you always want to, if you can, couch things in some same level of analytics. The trick with analytics is it's kind of a yin and a yang actually, and we talk about this a bit in our book. Is that you need the sort of domain and content expertise to interpret the analytics, but you also need the analytics to tell everyone when what they think is going on isn't true. So there's always a back and forth between trying to interpret the analytics and trying to bring domain expertise to the analytics. If that makes sense. Yeah, and users themselves do lie, especially when they're faced with an annoying survey. If you have to force them. Person just said go away. I've got a cool demo. It's actually an image search demo. It has nothing to do with NLP, but it's cool. Any other questions before I jump over that? Might have to go to my laptop here. So, okay. And then you can ask me questions about the demo. Okay, so we can tokenize anything into a search engine. In this case, we're working with images. And if you can see this is Python.
And basically, this is file IO, don't worry about that. Going to this directory, getting a directory of images, pulling them out, opening them. We're resizing them to 100 by 100. And instead of building tokens out of words, we're building tokens out of pixels of image. So we have the first thing here in this quote word is the position in the image. So we have 0, 1, 2, 3, so on. And then we have R, G, and E. And one thing you'll notice is we're actually dividing R, G, and E by 10. And that's, can you guess what that might be?
I got it back.
Dimensionality reduction?
Yeah, so it's basically dimensionality reduction. It's sort of similar to stemming, basically increasing the recall. So something that's reddish matches other things that are reddish. And I'm basically taking this and I'm dumping it into an Elasticsearch index with this field of EMP and all of these things. So we're building these giant, or 100 by 100 images, or 100 by 100 to 10,000 term. So if we go and what I'm going to do is I'm basically going to do a reverse image search where I'm going to search using an image. running through the same process. Think about this as sort of synonymous to the analysis process I showed before. And we could, if we were crazy, want to, bake this into the search engine and actually do it in the search engine. And what I want you to get out of this is this idea that what search engines, what specifically Elasticsearch sort of is, good at, is not so much thinking about language per se. It's good. Search engines are really good at doing this sort of distributed feature set. So we've got features that describe images, right? And we're going to search with something in the same feature space. Yeah, exactly. And the sneaky thing is there's only 6 images in there. Does anyone know a guy named Sujit Pal? Salmon Run, Silver Club. You guys should. So I gave this talk at Elasticon. He's actually, if you're interested in what I'm about to show you, you should go check out what he's doing, because he basically started with the dumb stuff I'm doing here. He's building on it. So what I do here is basically, I'm an idiot and I'm going to try to do some research. And what Sujit Pal has done is some really smart, cool stuff with feature reduction around images, but basically doing the same idea. So let me show you how this works. Cool. So if you see here, we are just calling this, basically giving the search function a URL, pulling it out, pretending it's a file IO, blah, blah. It's amazing how much file IO is so uses. Display it. We create a search that's basically the same function. So there's pictures. And we just tell Elasticsearch to search it, pretending it's text. And our very first search, if we do this, we search for this thing, which turns out to be fire truck. Hopefully Flickr never changes the URLs, just didn't know it was not working. And what's interesting when we search for this fire truck is we get back other red things. So it's interesting because it kind of works. We've got red here, red here, red here. And the most relevant result kind of has a similar background too. So it's like kind of pavement here, black, kind of pavement here, black, sky up here, sky up here. Whereas this one just has sort of green and maybe some stuff down there. And it's kind of a fun, sort of a fun thing to demonstrate some of the things that you could do with the search engine. It's interesting too if we think about problems like, how could we, well, first of all, how could we make this better? Yeah.
Get out a grayscale feature vector.
Yeah, so you could do some stuff around grayscale instead of doing like RGB, you mean?
Or not instead, but just add. So like if you searched with a grayscale version of the first picture, right now it would lose because there's no red, right? But if you also had call that a color insensitive version.
Yeah. Yeah, that's a good point. Could also do some stuff like at index time or in query time, we could like just see what the Google image recognition stuff recognizes, and there's some terms in here, round, wheel, car, and maybe this truck would go up because it's a truck. Okay. Now, it's interesting to think too how we might do this as a, what if people enter search terms? Could we map those search terms to a picture space? Or could we map the pictures to a term space and try to get them to match up? So basically what we're trying to do is get this features to line up.
How does something like this handle the linearity or the serialization, right? Because in a text document, it's clear, right? You're either left to right or right to left, top to bottom, right?
Mm-hmm.
In an image, I have meaningful sequences in 2 dimensions, right? So like it's not just a
That's a good.
it's
It's not just a line.
right. It's not just like a like what do they call it, like TVs, the line scan kind of thing. Like it's up and down. It's also diagonal. So how do I get? And like I'm assuming like things can get chained together, right?
I wonder if we could build. I wonder if you could like scan it a couple different ways and then treat them as positional queries.
Rotate, like at least a 90-degree rotate.
Yeah, or rotate. If all you did was care about cars, maybe you could rotate all cars into the same orientation.
I feel like you're like backing into the like confirms, like you know,
Yeah.
variance, almost the better beat over there, like things like that. You just like reinvent similar stuff. Eventually, it's that goal.
Right, and I don't pretend to be an expert at
I'm
any of this
not
stuff.
just making stuff up, but then you know, then eventually you get into like patches, you know, and
Yeah,
you get into like deep learning stuff. So I mean, it's like so it looks like the search piece is like a soup stone to getting into like machine vision, you know.
Yeah, or it's
Soup is machine vision.
or it's another way to. I think it's useful to think of it as if at the time that you need to answer the question, you can express images and queries in the same feature space and using whatever expertise is available. NLP is one set of expertise, image recognition is another set of expertise. The features of a home that you're selling for real estate is another set of expertise. And then what a search engine is giving, the power of a search engine is its ability to do this feature similarity at query time after all the smarts has been done and put into the search engine. That's kind of the, I
should have clarified that my goal is to not build a good image search. This is very naive. Yeah, it's very
naive. So this is intentionally very naive as an educational tool. So, yeah.
Actually, to that point, so I mean, I used to do some of the deep learning with images, but you need 1 million images and a person to basically validate the results. So it gets tedious, but yes, you get huge results. But what struck me here is this ability that, you know, just by simple rotation manipulation, you don't actually do any learning, but just as a get-go, you actually get some results.
Yeah.
So, I mean, machine learning is expensive. Right? It takes experts and it takes a lot of data. But this is my mind to code.
Yeah. Admittedly 6 images.
Sure. But I think that might be something, especially if you're a little bit clever about how you build your index.
Yeah. And a lot of what I do in relevance work is really feature engineering. Often around language, but often not at all around language. So, yeah, I'm sorry if I didn't clarify that I'm in no way an image search expert. So, I was thinking on the way up, another sort of fun thought experiment is how you could do image recognition this way. It's like, what if somehow you had a training set and you indexed the training set and said,
it's kind of like, I guess it's
basically like doing kind of what we're doing with the Google image stuff, which is also image recognition. But just as a fun thought experiment, like we had some training data, we indexed it, and we threw a truck at it with no term. We could return maybe some objects, some names of things like truck. Like instead of the search results being images, the search results could be words too that basically name the thing. So another sort of fun thought experiment that again is completely naive because I don't know what solutions to that. So either questions or curveballs or ideas. So like, yeah.
Okay, so even though it's so simple, I actually think it's really interesting that your term frequency analysis was not in here.
Yeah.
Because, for example, if you have a whole lot of images that are just blue in the top left or whatever is the sky, your TF-IDF or PM25 or whatever is going to learn that that those tokens are not important.
So yeah, that's a good point that doesn't get brought up often because I'm usually this is like I'm doing this at like the Python meetup or something. But the TF-IDF is actually really important because it's giving us the importance of like red or red in a pixel as a signal at search time. And TF-IDF is based around, Boolean queries plus TF-IDF are based around cosine similarity. Cosine similarity is kind of like, generic sort of similarity between different things of varying strengths. And we're basically getting cosine similarity, and TF-IDF is a good way of measuring sort of feature density. If we wanted to find something with a lot of red, if we said our search is red, and we actually turned that into a query that was just a giant red image, what would come back was all the red stuff to the top because of TF-IDF sorted by the proportion of pixels that were red. So TF-IDF is the future.
BM25.
Or BM25. Well, it's BM25 is basically TF-IDF.
Can you have too many features? Start to
You get
search
weird-
results noise. See noise.
You can overfit but you tend to overfit. You tend to overfit because you don't have enough features. I haven't gotten to that point where I've had I haven't honestly gotten to that point where I've got hundreds of things in the search engine and I'm trying to search over. But do you have experience with that?
No, it's just they were talking before he was talking about deep learning for image recognition, and in the process of training a neural network, you start off with very simple things like there's a line here, there's a line at an angle, and now the next layer might have a slight curve, and the next layer will have a circle, and eventually if you're doing face recognition, there'll be an entire face. If you're doing cat recognition, the entire cat. But it's all the pieces and parts that get to that point. And so if you could treat those lower hidden layers as features.
Right.
But then you start to ask the question, well, these next features are comprised of these features, and the next features of those features. So you're going to have all this overlaps. And, I didn't want to ask that question because it was very specific, so I asked maybe there could be too many features as a problem.
So what's interesting, one thing that comes up a lot in search and information retrieval is learning to rank. Has anyone heard of learning to rank? So learning to rank is basically, it comes up a lot, and a lot of people jump to it right away because it sounds cool, but it's often not the silver bullet that people think it is. But basically, if you have a lot of analytics data, and we just talked about how hard it is to interpret analytics, and you're really good at interpreting analytics. Let's say we have image search. And all we did was make it relevant enough with a couple of features. You can do basically classification around when you get in this query, which features matter the most in this kind of query, based on the features of the features that are shared between the image and the query in the document. What we call in our book signals. Someone jiggle the mouse. So that might actually help with that, because if you could just throw a bunch of features in it, do learning to rank, or maybe you start out with 5 features, and you do learning to rank, and you notice the correlation, and you sort of start to look at that, then you could suss out what actually matters.
That sounds like a lot of fun.
Yeah, it would be.
Have you been able to sell anybody on that so that way we can pay somebody here to do that?
Honestly, every time I give this talk, there are 5 good startup ideas.
Right.
And that's why Charlie's here.
Startup is kind of like a 4-letter word. Ideas is a letter word.
Yeah, right. I know, there's a lot of ideas. So, I haven't, that would be really cool. I have not done that. Played a little bit with learning to rank in normal search context, but in this sort of setup. I'm sure someone at Google is doing it, right? I'm sure they figure it out.
I mean, they're just the Plato's pen of well, if nobody here is doing it, they must be doing it, right?
Right, yeah.
They're Google.
Right, we just imagine someone at Google is doing something, they're way smarter than us.
Throw something out there. Google's only ever created 2 successful products, Search and Gmail. Everything else was a startup that Google acquired. I didn't say those are the only 2 products Google has ever created. Those are the only 2 successful products. everything from Android to YouTube to everything else. Ads started as someone else's startup that Google acquired.
So once we do this, Google will acquire us.
That is not a good exit strategy.
Google's got an image search.
Yeah,
It just
yeah.
doesn't work too well. You want one that does work well? And look up a company called Data Fission.
Data vision?
Fission.
Fission.
DATAFISSION. They're a startup
We
and
should start data fusion.
they're starting to sell some product.
They sound dateable.
Is that datable?
Shameless.
Oh, no. I thought you were like doing a count on my last name or something.
No.
Datable. I'm the datable.
One thing you could do to expand this a little bit would be, there's something called Code LDA, which is like text and pictures.
Oh.
So if you have captions, you can train on all
LDA,
pictures.
like
Right,
Yeah.
it's in Bligh's thesis. And then basically, you get a bunch of topics that are for the engine, for the image, and a bunch of topics that are for the text.
Yeah.
And so then you could use those to predict other images that don't have a caption.
That's good. Yeah, I'll still look that up. Any other thoughts or curveballs or? I'll take cockney insults.
Sure. So, like you said, idea, but you didn't really meet it with this data set, right? Because you have 6 images.
Yeah, that's
and your vocabulary size is giant. So you have whatever 256, so you divide by 25, Q percent, all percent. So your vocabulary size is enormous.
I mean, it's not that much. 25 times 25 times 25 times the positions. The positions are probably where it gets you. So you have 10,000 times. Someone do that. So like usable 6 million. Yeah. But if we could totally change that. If we just cared about color, we could decide that we would take that position out of it.
Right. Well, I guess you can do the position, what you did the RGB factor.
Yeah,
Which quadrant is it? Or which
yeah.
you know, like
And
rather than full resolution, so they're chopped down to
I
resolution.
think Sujit Pal, who I said sort of went with this earlier, I think he like divided it even further than that. He was like, you still get really good results at like 10 by 10 or something. It was surprisingly. So. There was actually on Hacker News last week. So it's really
Yeah, I got 2 more questions for you. One is definitely NLP related, one's not really. But they're both Elasticsearch and Lucene. So the first one is CJK languages. Chinese, Japanese, Korean, non-white space delimited, right? So you have, working with those languages, there's the additional step of